So, welcome back. Last class we studied several concepts and concluded our lecture on calculating the streamlines, the equation for the streamlines, and this is the slide where we finished. So, we will talk about more concepts now. If you remember that we said something about path line in our last lecture, that we are going to talk about it in the upcoming slide. So, what actually are path lines? So, path line is the actual path. Sorry, this should have been chosen the pen. Yes. So, a path line is the actual path travelled by an individual fluid particle over some time period. So, this is actually the trajectory of the particle, right. So, the real path on which the particle travels. So, path lines are the easiest of the flow patterns to understand, okay, and a path line is a Lagrangian concept. In that we simply follow the path of the individual fluid particle as it moves around in the flow field. So, what we are doing, path line can also be said as a Lagrangian concept, because what we do is we simply follow the path of an individual particle as it moves around in the flow field. Okay. So, for example, we see there is a fluid particle at t, that is t start, or we can also say t is equal to 0 for example, and the particle is moving like this. Okay. So, this is the path line, and if we want to know some intermediate at intermediate point, this is the intermediate point, and at the end this is t, and this is just to show you how the path line can look. It could be, the path line could be any shape, right, depends upon the fluid velocities and the fluid acceleration and the properties, but it is simply the path traced by the individual fluid particles. So, what we are doing here, we are simply following that particle as it moves along the fluid, therefore, it is a Lagrangian concept. Okay. So, a path line is the same as fluid particles material position vector, x particle, y particle and z particle t traced out over a some infinite time interval. So, we integrate and we can obtain that. Okay. Moving to the next concept, streak lines. So, what are streak lines? So, a streak line is the locus of the fluid particles that have passed sequentially through a prescribed point in flow. So, if we start tracing the fluid particles that have passed sequentially through a prescribed point in the flow, we will explain it a little more. So, streak lines are the most common flow pattern generated in a physical experiment. For example, if you insert a small tube in the flow and introduce a continuous stream of tracer fluid, for example, dye in a water flow or smoke in an air flow, the observed pattern is a streak line, because we are seeing the locus of that particle through a prescribed point in the flow, because that tracer is one specific point and we are following that movement of that particle. For example, this, if you inject a dye in case of water or smoke in case of an airflow, and there is an object here, and this is the particle in which we have injected the fluid particles, this one. So, it moves, this one, and this, if we observe this, the locus or the path traced by this particle is called the streak lines. You can always go to the YouTube and see one of these streak lines, and yeah, it's this figure shows the streak line formed by connecting all circles into a smooth curve. Okay. All right. Now, there is something called a stagnation point. So this is a very interesting point. So a point of interest in the study of kinematics of fluid is the occurrence of the points where the fluid flow stops. So as the name suggests, stagnation means something is stagnant or stopped. So those points are of very much importance. So one of the stagnation point could also be the plate, for example, because there also the fluid flow stops, right? So when a stationary body is immersed in a fluid, the fluid is brought to stop at the nodes of the body. Such a point where the fluid flow is brought to the rest is known as stagnation point. My one question to you is, what physical phenomenon helps or is related to the occurrence of the stagnation point? Suppose there is a solid object which is kept fixed in the fluid flow. When the fluid touches this body, that point is called stagnation point. Why? Because last lecture we read about a concept that was called no slip condition. Because of the no slip condition, the adjacent fluid particle, the velocity will also be 0 because of no slip condition. So this is the stagnation point. In this example, in this figure 4, there is a wall here, okay, and when there is the air flow or the fluid flow, whatever you want to call it, is there. When it encounters the wall, the velocity here actually is 0, right? The flow is stopping or diverting. So in this direction there is no flow, and this is called the stagnation point. All right. Thus, a stagnation point is defined as a point in the flow field where the velocity is, this is the key point, is identically 0. This means that all the components of the velocity v, that is u, v and w, are identically 0 at this stagnation point. Some of it we were going to see in today's lecture, or maybe in the weeks coming forward, what the stagnation point, where it can be used. Now after all these points, we move on from the velocity description to the acceleration part. Okay. So acceleration, first thing that you already know, is a vector. In natural coordinate system, that is, we describe the acceleration along and across the streamline that we are going to see. Okay. Suppose this is a streamline here, this in figure 5. Let me take the laser pointer here. Okay. So this is a streamline, okay, and this is a direction s, okay, and this is the velocity v direction here, and this is the s direction, change in velocity in s direction, and this is the velocity change in the direction perpendicular. Okay. All right. So acceleration can be given as, so I will go back to the pen, total derivative of velocity with respect to time. Okay. dv dt and not del v del t. Okay. So the total derivative of the velocity is called the acceleration. In our case here, it will be a vector sum of the acceleration along the streamline and perpendicular to the streamline, same as velocity. Suppose the velocity, there are two velocity directions, vs and vn. So total velocity, the speed is going to be vs square plus vn square whole under root. Great. So in the tangential direction, this direction, in the tangential direction, as can be written as del vs by del t plus vs del vs ds. This you already have derived in your fluid mechanics class. Sorry. Okay. So this is the acceleration in s direction. all right. And in the normal direction, it's nothing that it's del Vn by del t plus Vs square by r. Vn and Vs are velocities in s and n direction. Okay. All right. Here this r is the radius of curvature of the streamline at that point. This we will solve some problems maybe in the upcoming lectures. Vs is the tangential component of the velocity v, this we already talked, and Vn is the normal component of the velocity generated due to change in direction. So, normal Vn, the velocity component that is normal. The term del Vs by del t and del Vn by del t, this one and this one are called local accelerations. Okay. And Vs del Vs by del s is the tangential convective acceleration, and Vs square by r is the normal convective acceleration. Okay. So, this is quite some information to note. So, now what I am going to do, highlight the most important one. Okay. So, let us go to the previous slide. So, this is an important equation. So, it is a combination of As is a combination of local acceleration plus convective acceleration. Okay. In the normal direction also, it is a sum of local acceleration plus the normal, this is also normal convective acceleration. Okay. So, when we need to calculate the total acceleration, we should be calculating the corresponding accelerations, local accelerations and corresponding normal convective accelerations and the convective accelerations which is tangential, and then we will be able to solve the problems. So, again in Cartesian coordinates, if we write the velocity, I think it is best again to write V as u I cap. Here we have written the velocity, the coordinate, I mean I cap j cap before, it is also right, but it is better to, this is the normal convention. Okay. Acceleration Ax, Ay and Az in the x, y, z directions respectively are. So, Ax will be written as del u del t plus this is local acceleration and this part is convective acceleration. Okay. So, let me rub the ink. Similarly for Ay as well. So, del v del t plus u del v del x plus v del v del y plus w del v del z. These are in some important equations that you should be remembering. Az will be del w del t plus u del w del z. So, you see u for Ax, v for Ay and w here for Az. Okay. So, now we will see a practice problem. Okay. So, the question is, the velocity along the center line of a nozzle of length L is given by V is equal to 2t 1 minus x by 2L whole square, or I will write 2t 1 minus x by 2L whole square. Okay. Here the V is velocity in meters per second, time t in seconds, and x is the, so t is from t is equal to 0, x is the distance from inlet to the nozzle. So, and so we have to find the convective acceleration, local acceleration and total acceleration when t is equal to 3 seconds, x is equal to 0.5 and L is equal to 0.8. So, we have seen the equations previously, and that we are going to utilize now. So, the solution procedure goes as like this. Local acceleration is given by del v del t. Okay. So, del v del t, if you see this equation here, so if you multiply, if you do del v del t, it is going to be 2t, this t will, this will become 2 times 1 minus x by 12 whole square, and that is what exactly this is. And at t is equal to 3 second, and at x is equal to 0.5 meter, what we have done is we have substituted the value of t is equal to 3 second and x is equal to 0.5 in this equation. So, it is 2 will remain 2, 1 will remain, x is 0.5 and length value we have been given 0.8, and this comes out to be as 9.945. very simple multiplication is there. Okay. This is the local acceleration. So, now the convective acceleration here is going to be, you see there is only one direction x. So, there will be only one velocity component, I mean convective velocity component, and that is going to be v del v by del x. Okay. So, if v was, so we knew that, I mean the original equation says 2t 1 minus x by 2l whole square, right. So, when we multiply v del v by del x, so let us write down v. So, this is v, correct, 2t into 1 minus x by 2l whole square. And what is del v del x? So, if you differentiate del v del x, 2t will remain 2t, okay, and this 2 will come down here on here, and it will be 1 minus x by 2l multiplied by this x will become minus 1 by 2l, and on simplification I will just erase the, so this on simplification will give minus 4t square by l into 1 minus x by 2l whole cube. So, what needs to be done? Very simply we need to substitute the value of t, l and x to get our, so substitute the value of t, l and x to get convective acceleration. So, at t is equal to 3 second and x is equal to 0.5 meter, convective acceleration will be minus 14.623 meters per second squared. So, the total acceleration is going to be local plus convective acceleration. You can simply do the arithmetic sum. I generally prefer to write these accelerations separately. So, if you write this one and this one separately, it is fine. Here we have simply added them because the total is the sum of both the accelerations. Okay. Very nice. So, going to another concept, that is continuity equation. So, in one dimensional analysis, what we see is in steady flow, mass rate of flow into the stream tube is equal to the mass rate of flow out of the tube. So, whatever comes in goes out of the tube, for example, okay, in a steady flow. So, in one dimensional, the continuity equation says rho 1 A1 V1 is equal to rho 2 A2 V2. This is the continuity equation. For incompressible fluid under steady flow. So, steady flow we know that not a function of time, but what is incompressible fluid? Density remains constant. Okay, so if the density doesn't changes, so rho 1 will be equal to rho 2. Okay. So if there is V1 and this is the velocity V1, this is the cross sectional area A1, this is the velocity V2 and this is the cross sectional area A2, and for incompressible fluid, because rho is equal on both sides, we can get it cancelled and we can simply write A1 V1 is equal to A2 V2. So this is the continuity equation in one dimension. Now when there is a variation of velocity across the cross section of the conduit for an incompressible fluid discharge like this, you see, so if this velocity, you see this is the velocity component, this is V and this is cross sectional area 1, this is cross sectional area 2 and this is the profile. We can simply write still the equation of continuity will hold, but what we do instead, because the velocity is varying across the cross section, so instead of writing V1 A1, what we do is we integrate the velocity with area for the entire surface and do it on the other side as well. So let us say if this is this side A1 and this is the other side A2. No change, just that we have to use a differential or an integral form here. Okay, all right. So we were going to see a practice problem. Now this figure we are going to shows a pipe network with junction nodes at A, this is junction node, B, C, D, E and F. The numerals in the figure like this 100, 30 indicates the discharges at the node or in the pipes as the case is, and the arrows indicate the direction of the flows. So this, let me just erase this one now. So you see this means that the flow is in this direction, okay, and this means this flow is in this direction, but many of, like here it is already told that the flow is in this direction, but other places we have to calculate. Okay, so the question is, by continuity equation determine the missing discharge values and their direction in the pipes. So we are lucky because they have directly given us the discharge value, and that is what we have to preserve. A1 V1 is discharge. Okay, in the pipes AB, which is unknown to question mark, BC, CD and EF. Actually we can calculate BF, BE as well, BE, yeah, okay, all the 5. All right, so we go to the solutions. So by the continuity criterion, this is quite important, the flow entering into a node must be equal to the flow going out of the node, as the equation of continuity says. Thus by considering the flow, so what we do is we consider flow into the node as positive, and flow out of node as negative. So at point, so there is a point here, and whatever goes in, for example x goes in and x by 3 and 2x by 3, whatever goes in will go out because of the equation of continuity. Therefore what this implies is that the algebraic sum of the discharges at a node is 0. This is quite important. So this is the fundamental that we calculate. Thus at node A, so let's go back and see. If we assume this is we call QAB. Okay. So 100 is coming in and 70 is going out, and QAB is also going out. Okay. If we consider this node here, okay, let me just erase this, sorry, this node A. So 70 was here and we assume QAB here. So this will be 0. So this is reflected by the equation here, 100 minus 70 minus QAB is equal to 0. So what we get simply using this equation, QAB is 30 and is from A to B. Okay, very simple. So first now we go to node D. This is node D. So if we calculate, if we see, so 50 is also coming in this direction, 70 is also coming into this direction, and there should be something here that is called QDC, I think. Okay. So 70 plus 50 minus QDC is equal to 0, therefore we get QDC is equal to 120 and it is from D to C. Similarly, at node C, you go to node C, let me erase this, this is node C, this we have already calculated, right, this was in this direction 120, this we already know, and this for example we need to calculate QCB or QBC, whatever it is there. So this is known and this is unknown, right. So this is 120 going in, 80 was going out and QCB was also going out, therefore we get QCB is equal to 40 and it is from C to B. Okay. Now going to the node B. Node B. So now this is known, this is known, this is known, this is known, and we need to calculate this one. So most of the things are known for node B, because node B will have incoming from here that we have already calculated, this we just calculated, okay, this we know from before, and this is already given as 20. Okay. So for node B, 30 plus 40 minus 30 minus QB minus 20, and this is going to give QBE as 20, but direction is from B to E. Okay, let me just erase all the ink. And finally at node E, if we go back again to node E, right, this is we know, this is we know, now this is also we know from our last calculation. This is the one that we need to calculate now. So only one unknown is there. So 80 plus 20 minus QF minus 90 is equal to 0, and this gives us QEF is equal to 10 and QEF is from E to F. Alright. So at node F we need to calculate our final quantity QF. Then see, that is simply discharge out of node F. Okay. So we know this, 10 was coming here, so 20 plus 10, and that will be simply 30. So simple application of continuity equation, that comes 30. Now the final distribution of the discharges are in as follows. I will just take you 100 goes in, 30 is distributed, 100 goes in here, 30 distributed here, 70 comes here. Now 50 plus 70, the 120 will go here. And at node C, 80 is going in this direction, 40 is going in this direction. At node B, 30 which is coming here will go there, 40 that is coming here is distributed 20 this side, 20 this side. Okay. At node E, 80 is coming in this direction and 10 is going in this direction, however we are also getting 20 from this direction, therefore resulting will be 90. So at node F, what is happening is we get 20 from this side, 10 from this side, and this total 30 is going from this side. So every place the equation of continuity is satisfied. So this is one of the simplest most problem that you can see about the equation of continuity. Normally this could also happen in place of the velocities, only the velocity can give, and the areas of these pipes could be different, but the procedure will remain the same. You have to calculate A1 V1, A2 V2 and so on, and equate the discharges as we did here in this simplest example. So this is for today. I am going to see you again in the next class. Thank you so much.